Okay, this is the final video in a series on rings in algebras, and here I will introduce two concepts. The minimal ring containing a given family of subsets and the minimal sigma ring containing a given family or collection of subsets. So imagine we have a collection of subsets which is non-empty, not necessarily a semi-ring, any collection of subsets. Now the symbol R of S will represent the minimal ring which contains this given collection of subsets. The fact is, in fact, that this minimal ring does exist. You can easily see this by just saying that this minimal ring is the intersection of this sort. It is the intersection of which is taken over all rings containing the collection S. It is relatively easy fact to see that actually if you have two rings, any rings of subsets, if you take their intersection, it will be a ring again. So by taking this huge intersection over all possible rings containing this given collection, it will be another ring. The only thing which you have to emphasize here is that this intersection is taken over non-empty family of rings. This is because actually this large, very rich ring, collection of all subsets, is among this class of rings, because it's a ring and it contains this collection S in it. So this is what we will call and how we define the smallest ring containing given collection S. Similarly, you can define the smallest sigma ring containing the given collection S, and that's how we do that. We take now the intersection, but this time we take the intersection over all possible sigma rings containing a given collection. Again, this intersection is non-empty because at least this ring will be among this class of sigma rings we run our intersection over. Now, these two identities, they show you that these constructs, the smallest ring and the smallest sigma ring, they have the right to exist. They actually exist. However, from the practical point of view, we need some constructive approach to these two things, to this minimal ring and minimal sigma ring. In this regard, the following observation is very helpful. In general, of course, you can't say much about these constructs, but if you know that S, not just any collection of subsets, but a semi-ring, then the minimal ring containing a semi-ring has precisely this description. And the proof of this lemma is in fact given in the previous video, because in previous video we showed you that this kind of collection will be a ring, given that S is a semi-ring. If it is a ring, it will be here among this intersection. And clearly it is the obvious, obviously it is the minimal ring, because any ring which contains S, it will have all possible disjoint unions of the elements of S. So any ring, any possible ring which contains a collection S in it will have all of these sets in it. So it will have in fact this set in it. I'll leave the details for you to figure out. Now, when we look now at the minimal sigma ring, here the structural nature of this minimal sigma ring is far more complex than this one. In fact, I have this sentence which says, unfortunately, the minimal sigma ring containing given collection S does not have a nice structural description, even if S is a semi-ring, even if S has its own structure. There is a sort of half structural description of this ring, and that's something which I describe here. You can describe this minimal semi-ring as a union of the collections like this. Collections R sigma n. And these collections R sigma n, they are constructed like this. The first R sigma 1 is just your initial set, initial family S, initial collection S. And every next one you define inductively by saying every next one will be the collection of all possible countable unions, countable intersections and set differences where AK, A and B are elements of your previous collection. In fact, I have to correct myself. Not countable intersections, but finite intersections. Finite intersections. I mean, the validity of this description comes from the nature of the rings, because rings are something which are closed with respect to set difference, finite intersections, and sigma rings, and countable unions. And that's why you just take your set S. On the first round, you take all possible unions of the elements of S, all possible finite intersections, all possible set differences. You come up with the set. Now, in the next stage, you take now the elements of your previous set and do the same operations. It can be shown with the help of mathematical induction that by doing this construction, you will end up with a minimal sigma ring containing given collection S. And your collection S does not need to be a semi-ring in this construction, unlike, for instance, this one. However, this structural description, it is sort of a structural description. It is far more complex than this nice one. This is an objective fact of the nature that this minimal sigma ring containing a given collection, even if this collection is semi-ring, doesn't have a nice structural description. This is something we're going to struggle with a little bit later by introducing far more interesting constructs, but let's just wait until then. In the second part of this video, in the second part of this slide, I will actually show you that this is not, I mean, I said this a few times, but I didn't really give you any convincing argument for that this minimal sigma ring is not, in general, doesn't have any nice structural description. For instance, you might probably guess that the set like this, just by modeling from this example, if I take all possible disjoint countable unions of the elements of your semi-ring, you may ask the question whether your minimal sigma ring will be equal to this. Unfortunately, this is not true. By looking at this example, you might think that this minimal sigma ring may have this kind of description. Unfortunately, this is not true. This set is a subset of the minimal sigma ring, but in general, it is not equal to it. And I have this nice demonstration which will convince you that this is true. If I take this semi-ring of half-open intervals, and if I just give a name to this set, I'll call it R, so it will be the collection of all possible disjoint countable unions of half-open intervals. I will show that this is not a ring. I'm going to do it by doing it like so. Imagine for a sec that the closed interval 0, 1, segment 0, 1 belongs to this set. I want to show this cannot happen. Indeed, if this is so, then the closed interval has the representation via disjoint union of half-open intervals, which means that, for instance, point 1 falls within one of these half-open intervals, so there is one n, such that unity belongs to one of such intervals. But because the interval is open on the right-hand side, it means that there is an epsilon such that not only 1, but everything from 1 to 1 plus epsilon, including 1 and including 1 plus epsilon, also belongs to this specially chosen interval. It's just the nature of the half-open intervals. And then, if it is so, then this will also belong to the whole disjoint union. So, in fact, the interval 1 from 0, because the first part also belongs to this disjoint union, to 1 plus epsilon belongs to a subset of this disjoint union. But the disjoint union was originally the interval 0, 1. And we have a contradiction. We have some bigger interval is a subset of a smaller interval. So this is not true. This set, this collection, doesn't have the interval 0, 1. Now, on the other hand, I'll show you that if R is a ring, if it was a ring, then I can represent the interval 0, 1, closed interval 0, 1, like this. It's a very nice representation for the closed interval 0, 1. Look at this. I take the half-open interval 0, 2, and I set difference this with the disjoint union of these half-open intervals. It is a little bit of an effort to see that actually this is a true identity. So if this was a ring, each of these half-open intervals individually belongs to this ring, or in fact this disjoint union by the definition of this R set is a member of this ring. This half-open interval also a member of this ring, so the set difference, if it is a ring, also belongs to this R. So altogether we conclude that this 0, 1 must be inside this collection R, but we just saw it cannot be so, which means that this assumption is wrong. This particular R is not a ring. This is a good example how to show that a given collection is not a ring. And that's not a trivial example.